In this video, I'm going to look at text data types in Python, exploring the Python data model further. So I'm just going to open up my Windows PowerShell, which has mini-conda initialized, and I'm going to activate my Spyder. So I can use the directory function to retrieve a list of strings where each string corresponds to an identifier name. And if I have a look at the object class, I see we've got these data model identifiers. And in the previous video, I gave a detailed overview of these. So what I'm going to do now is have a look at the directory of the string class. And notice that we've got many of these same data model identifiers. And the string has the design pattern of an object because it's based on the object. And this becomes more apparent when we reorder the data model identifiers. So recall that the string's method resolution order is string and then object. And this means the string has the design pattern of the object and therefore has all the data model identifiers found within the object. So we can have a look at the string's docstring, and this uses the doc data model identifier. And if we have a look at these additional data model identifiers, and the collections.abstract base class, we get more details about the design pattern of the string. So the string is essentially a sequence. So notice that we've got all these additional data model methods. So what we can also have a look at is the help. And if we look at help of object, we get an overview of all the object-based data model identifiers. So recall that the data model identifiers are defined in the objects class, and each data model identifier defines the behavior of a built-in function or an operator. And now we can have a look at help of the string class. And this gives us an overview of all the string identifiers, starting with the data model identifiers and then the string specific identifiers. And these identifiers are called directly. They don't have any equivalent built-ins or function. So if I type in string with open parenthesis, I see the string's initialization signature. And I can supply initialization data in the form of a string. And if I press enter, I'm going to create a new string instance. Notice that this isn't assigned to a variable, so therefore the return value is displayed in the IPython console. If we assign it to the variable text, it will display in the variable explorer, and we'll see it's the type string and it's got the size 12, meaning there's 12 Unicode characters in this string. So new has created this instance self, which we refer to as text, and we've initialized this using the provided data, hello world, exclamation mark. So we can use the built-in type to determine the class of the object text, and we see it's a string, and we can use length to determine the length of the string, which is 12. For clarity, I used the string class to instantiate an instance of the string class. Now the initialization data was provided as a string. And because string is a built-in, there's a shorthand way of instantiating it. So we can just use the single quotations. So this object name text displays in the variable explorer, and we use this object name to access the object. Now if I delete this object name, notice it disappears from the variable explorer. So we can no longer use the object name to reference this object. So to recap on assignment, let's create two object names, text1 and text2, corresponding to the strings 1 and 2 respectively. So recall that the object name can be conceptualized as a label. So what I'm going to do now is use this label to access the item, which is a string 1, and assign this to text. So conceptually, the string 1 has two labels, text1 and text. And now I can use text2 to access the string 2, and I can reassign this to text. So conceptually, this is taking the label text from 1 and placing it on 2. And now if I delete the object name text, notice that 1 and 2 are uninfluenced, because deleting the label does not delete the object. However, when all labels pointing to the object are deleted, then the object becomes orphaned and is cleaned up by Python's garbage collection. So we've seen that we use single quotations to enclose a string. Now, if we want to incorporate these within a string, notice that the syntax highlighting changes between a string and then object names and then a string. If we use the left slash, we can insert an escape character, and this means incorporate the quotation as part of the string. So in the variable explorer, we see the string contains a string literal. And if we view text in the IPython console, we see that it's enclosed in double quotations. Notice that we can use double quotations to enclose the string, and that it's equivalent. However, the IPython console uses the preferred default representation of a string, and therefore displays the string using single quotations. And a general tip to write good code is to try and be as consistent as possible with the default formal representation. So as we discussed, string is a built-in, and normally we don't use the string class to create a new instance. However, the string class is typically used as a casting function, i.e. to cast from one built-in to another built-in. So for example, this whole number, which is the integer 1, can be cast into a string using the string class, and notice that when we do so, it's got quotations around it, indicating that it's a string. Now these two look the same on the variable explorer, and this is because the variable explorer only shows the data for the string, it does not show the quotations enclosing it. However, the color coding of the variable explorer makes it obvious that these two are different data types. And both the string and integer class follow the object-based data model, so we can use type to determine their class. So we see we've got the type string and the type int respectively. So instead of a whole number, we can have a look at a floating point number. And once again, we can cast this to a string instance using the string class. We can also cast a Boolean value to a string. So recall that the Boolean instance false is essentially an object name. And when we cast this to a string, we see quotations around it. There is an additional text data type called a byte, and we can create a byte instance by using the prefix b. So the color coding and type on the variable explorer indicate that these are different classes. And we can use the string class to cast a byte into a string. And in order to do so, we need to supply the bytes encoding, and the default is UTF-8. This will later be discussed. So the object name text returns the string hello, and notice there's no prefix b. The object name btext returns the byte string hello, and notice it's got the prefix b. Let's now have a look at a collection, such as a tuple. And we can cast this into a string using the string class. So this is essentially the text that we type to make the tuple. It gets enclosed in quotations. And because this tuple contains a string instance, i.e. a string literal, then double quotations are used to enclose this. Okay, so we've seen how we can use the string class as a casting function. And now let's reassign text to hello world. Notice that hello world displays in the variable explorer. Now, instead of using a space, if I type in /t, which is an escape character for a tab, notice that hello tab world displays in the Variable Explorer. So if we use the object name to return the string into the IPython console, we see this escape character and quotations. If instead we use the print function to print this to the IPython console, we see that the escape characters are processed and the quotations enclosing the string do not display. So we've got the informal and formal string representations. So the informal string representation defines what the string class does to the string, so it should leave it unchanged. And if you have a look at the formal representation, you see it's got double quotations enclosing the single quotations. So this means the single quotations are part of the string itself. And if you have a look at the escape character, it's got // which means insert the / as an escape character. So when this is printed, the escape characters are processed, and therefore the double quotations disappear, but the single quotations are part of the string, and the now single /t are part of the string. So when we print the formal representation of the string, we see what's displayed typically when we return the string to the IPython console. So we had a look at the abstract base classes, and we've seen that the string is a sequence, and it's a sequence of Unicode characters essentially. So we can have a look at this Datamodel method contains, and this defines the behavior of the in operator. So instead of typing in this, we can see we've got key in self. So in this case, the key is going to be h, and self is going to be the object name text. So we can type in h in text, and we can see that this is true. And so we can have a look for the key lower h in text, and we can see this is false. So recall the string has a length of 12, meaning it's got 12 Unicode characters. We can create an iterator from the string, and an iterator displays only a single value at a time. So because every character in the string is an ASCII character, this shows as an ASCII iterator object. So essentially, when we call next on the iterator, we consume a value and the iterator moves to the next value. So if we keep going through, we're going to go through every single letter in the string, and then we're going to get an error message once we've exhausted the iterator. And now I'm going to use a new string for text that has ASCII and non-ASCII characters. So the ASCII characters are essentially the characters used in the English alphabet, and the non-ASCII characters are, in this case, essentially the Greek characters. So the spaces and exclamation mark are ASCII, and the Greek characters are non-ASCII. And if we count each of these characters, we can see that the string length is 14. So if we create an iterator from this and step through it until it's exhausted, notice the subtle difference that this is a string iterator instead of an ASCII iterator. So moving down, we've got the Datamodel method identifier length, which defines the behavior of the built-ins length. And in this case, we return a length of 14. And this displays on the Variable Explorer as the size. For visualization purposes, I'm going to cast this string instance text into a tuple called archive and open it up within the Variable Explorer. So notice that each value in this tuple is a Unicode character, and it's a string with the length 1, and each value corresponds to an index. So we can use the data model identifier getItem to retrieve the value at this index. And instead of using this data model identifier, we normally use square brackets to enclose the index. So if I press Ctrl, Shift and Enter, I can type in multiple commands in the IPython console. And let's create a start of 0, a stop of 5 and a step of 1. And here we can create a slice using the start, stop and step. So let's just assign this to the variable name selection, and we can index using this selection. So if we start from 0, we're going down in steps of 1, and in this case, until we get to 5, but we don't include 5, 0, 1, 2, 3, 4, up to 5, but excluding 5. So that's why we've got these 4 Greek characters followed by a space. Now, instead of explicitly using a slice object, we can use the colon operator. So here we can separate the start, the stop, and the step. So the start, the stop, and the step have default values. The start has a default value of 0, the stop has a default value of the length of the text, and the step has a default value of 1. So notice that the length of the text, as we've seen before, is 14, and the last index is actually the length minus 1. And this is a consequence of using zero-order indexing. So essentially there's 14 values, but one of them has the index 0, so the last one is at index 13. And as a consequence, when we slice, we are inclusive of the start bound and go up to but exclude the stop bound. So in this case, we're starting at 0, going up to 14, but not including 14 itself in steps of 1. Now, because these values have defaults, we can simplify the indexing. So if we don't specify the step, the default value of 1 is going to be used. And if we don't specify the start, the default value of 0 is going to be used. And if we don't specify the stop, the default value of the length of the string is going to be used. And because the variables assigned are the same as the defaults, all the above create the full string. Let's go from the default stop of 0 to the length of the string minus 1. So we essentially return everything in the string apart from the exclamation mark at the end. And if we use a colon by itself, we return the entire string. So the string doesn't have the data model reversed. However, it has the data model method iterator. So what this means is there's no special instructions for creating a reversed iterator. And we can use the builtins function reversed to create the reversed iterator. And notice that when we use next, we step through the values of the iterator from the last index going down to the 0th index, and get the stop iteration error message when the iterator is exhausted. So let's have a look at using a different step size. So we can use a step size of 2. And we can start at 1 using a step size of 2. If we use a step size of -1, we actually have a different start and stop default value. And we reverse the string. So if we use the default value of 0, notice that we're only getting a single character. And instead, if we use the negative default start value of -1, we retrieve the entire string in reverse. And the default stop for a positive step is the length of the text, but notice that this gives us an empty string. So we can change this to the negative length of the text, but notice that we don't get the first value. and this is because we're using zero order indexing, and we go down to but exclude the stop bound, so we need to offset this by -1, and now we return the reverse string. So an iterator is normally implicitly used in a for loop. Let's have a look at construction of a for loop using a range object. Now the range object is very similar to a slice object, so it's got a start, a stop and a step. And in this case we're going to set the start to 0, the stop to the length of text and the step to 1. And we're going to print the number. So notice that each integer printed here matches the index in the tuple of the string displayed to the left. And the range object, like the slice, has a default step of 1. And it's got a default start of 0. So in the examples above, you don't see any changes using this shorthand notation. So let's now construct an iterator. And what we're going to do is we're going to use next on the iterator within the for loop. So it appears I've made a bit of a mistake here, so I've got a missing parenthesis. So now we see that each character is printed using the for loop. Now instead of using the iterator, we can just use the string directly, and we can change this variable name to make more sense, changing it from number to letter. So behind the scenes, the iterator is essentially used when going through the for loop, but the syntax shown is a lot more elegant. And if we want to have both the index and the letter, we can enumerate the text. So notice that we get both the index and the letter. And if we want the negative index, we can change this print statement to be index minus the length of text. And this shows you the negative index of each character in this string. So the last value is -1, and the first value is minus the length of the string, which in this case is -14. So the string has the data model method hash, meaning the built-in function hash can be used on the text object, and notice that this returns an integer. Now, because the string is hashable, it means it can be used as a key in a mapping. So let's just have a look at some example mappings from matplotlib. So we've got these strings to the left, and they're used to index into the mapping to retrieve the object that each key is associated with. So in this case, using the key B retrieves the tuple associated with this key. And the key Alice Blue, notice this is a string that's easy to remember, retrieves another string. Notice that this is a hexadecimal string and it's quite hard to remember. So another consequence of having a hash value is that the string is immutable. And what immutable means is once a string has been created, it cannot be modified. So all these methods listed to the left are immutable and therefore will have a return value. So they'll return something, and the original string that they're called from will be unmodified. So we can use the data model method getAttribute to get one of the attributes using its string. So we can get the attribute of the data model method length. And for short, we can use getAttribute. And notice, because we've got this attribute, we can call this. So if I have a look at the directory of text, notice that I get a list of strings. So getAttribute is used in this kind of format, normally within a for loop. Normally an attribute is accessed from an instance using the dot notation. But because the data model method length controls the behavior of the built-in function length, the built-in length is therefore preferentially used. Notice that we've also got set attribute and delete attribute. However, both of these don't work for the string class because it's immutable. So when you attempt to use these, you're going to get an attribute error telling you that the string is essentially read-only. The string class has the 6 comparison operators, and the string class is actually ordinal. And this can be seen better by examining a single character. So if we take this character and use the ordinal function on it, we retrieve the integer that the specific character is mapped to. So notice that these two characters have different ordinal values. And so if we use a comparison operator such as greater than, we get false in this case. And what we're actually computing is essentially it's the ordinal value of the first value greater than the ordinal value of the second value. So in this case, it's false. So one thing that you might find unexpected is the ordinal value of a lowercase letter is larger than the ordinal value of an uppercase letter. And therefore, it's not true that big A is greater than small a. So this is comparing these two values, 97 and 65, where 65 corresponds to the uppercase A and 97 corresponds to the lowercase a. So now we can compare a string of characters. So what we essentially do is a character-to-character comparison. So A is going to be equal to A, B is going to be equal to B, C is going to be equal to C, D is going to be equal to D, and then we've got a comparison between E and F. And the ordinal value of F is greater than the ordinal value of E. So this statement is false. Now, if we compare strings of different lengths, once again, we're going to compare each character. So A with A, B with B, and in this case, D is going to be compared with C, and the additional D is going to be ignored. And if we compare ABC with AB, A is equal to A, B is equal to B, and then we're comparing C with no character. And having a character is greater than not having a character. So in other words, if we have a look at A and compare it to the empty string, we see that the character A has a greater value than an empty string. So the string also has some data model methods that correspond to operators that aren't seen in the object class. And we can get some more details about the operators using the operator module. So if we have a look at operator dot __, we see a number of data model identifiers which each map to an operator. So for example, there is add, which is defined to concatenate the instance self with the instance value. So in this case, the instance self is text and the instance value is the string hello. And typically we use the operator to do this. And one thing to note is that concatenation doesn't include spaces. So if you want a space, you're going to have to manually concatenate this as well. The data model methods add is defined in both the int class and the string class, and it performs a different operation. So notice that in the int class, it performs numeric addition, and in the string class, it performs concatenation. So 1 add 2 is 3, and the string of 1 add the string of 2 is 12. And note that this is the string of 12. And if we try and add the string of 1 to the int of 2, we're going to get a type error. And this is because Python doesn't know what to do with these two different instances. The data model method multiplication is configured in the string class to work with an instance of the integer class for the purpose of string replication using the multiplication operator star. So notice that this string is replicated 3 times because it was multiplied by the integer 3. There is also the reverse multiplication operator, and this allows multiplication of a string by an integer instance, once again performing string replication. So text times 3 is forward multiplication, and 3 times text is reverse multiplication with respect to the instance of the string class. The string class also has the data model method modulus, which defines the behavior of the modulus operator, which we also know as the percentage sign. And this is essentially used to insert a variable into a string. So let's just create this base string, and we want to insert 3 variables, so we're going to replace these variables with percentage signs. And then we can add a format specification behind each percentage sign. And let's just assign this to the string base. And we've got variables. And we can create a tuple of variables, in this case 3 different numbers. And more details about these format specifiers are given in the string documentation using the format specification mini language. So here we see D as a decimal integer, and we can see that F is fixed point notation and G is general notation. And then you see a number of examples. And now we see that the data model method modulus can be called from base and defines the behavior of the modulus operator, which we also know as the percentage sign. So notice that these 3 numbers are inserted to the string, and each number is formatted as specified. So 1's inserted as a decimal integer. The second number's shown in the fixed format, rounded to 3 figures after the decimal point. And then the third number is shown in the general format using 3 significant figures. Now, although the string class has a reverse modulus operator, it's unsupported, and this is because the syntax doesn't really make sense using this operation in reverse. So the method reverse add isn't defined because the data model method add works between 2 instances of the string class. And with respect to the operator, the string instance to the left side of the add operator is the instance self. And the instance to the right hand side of the add operator is the instance value. So we also have the data model method format, and this defines the behavior of the class when used within a formatted string. So in this case, it will define the behavior of a string within a formatted string. So think of this data model method as defining the behavior of the format specification language for the string when used within a formatted string. So the string class has the 2 methods, format and formatmap, which can be used to create a formatted string. So essentially, where you want to insert variables, you use braces. And the number of variables to be inserted using the format method must match the number of braces within the base string. So each brace can also be numbered positionally. So 0, 1, 2, and 3. And we get the same results as before. We also have the flexibility to insert a variable in multiple places by using the positional input argument multiple times. And we can use a colon to specify a format specification for each variable being inserted. So I'm just going to increase the number of trailing zeros as we go from left to right, just for clarity. So D means decimal integer. The 1, 2, 3, and 5 mean the number of spaces that the decimal integer should occupy within the string. And if these are preceded by 0, then the trailing zeros will display. So if I repeat the 2 lines above without the 0, notice that the trailing zeros don't show, but the width taken for each variable is the same as in the case above. We also have the option to use named parameters within the base string. And when we use the format method on the base string, we're going to need to supply each of these named parameters and assign each of them to a respective value. So this form is very similar to a Python dictionary. And what I'm going to do is create the dictionary instance mapping. And now that we have this, we can use the format map method instead of format and supply the mapping as the input argument. So we've created a base string and used the format method on it in a separate line. So instead of doing this, I'm going to combine the 2 lines together. So if you look at the 2 lines combined together, and you have a look at where the numeric instances are in yellow, and if instead you have the variables 0, 1, 2, and 3 in the global namespace, which show up in the variable explorer, you would essentially have 0, 1, 2, and 3 in the placeholders, and then you have 0 equals 0, 1 equals 1, 2 equals 2, and 3 equals 3. So you're essentially typing in each variable name 3 times in order to insert it. And this is very cumbersome. So there's a shorthand way of doing this known as an F string. So in order to demo this, I'm going to need to create the variable names 0, 1, 2, and 3 in the global namespace. And now if we just type in the base string, and I'm going to remove this format method and prefix it with F. So notice we've got 0, 1, 2, and 3, and these are shown in white because they are object names. And the values that each corresponding object name is assigned to will be inserted into the F string. So in essence, the F string is essentially a shorthand way of creating a formatted string using the format method. So 2 methods in the abstract base class for a sequence are count and index. So count essentially counts the number of times a substring appears within a string. So for example, if we look at text, we can count the number of times one of these letters appears. And actually each of these letters is unique because of the accents. So let's also have a look at hello and count the number of times the substring L and the substring O appear. So this is 2 times and 1 times respectively. So count has some optional input parameters, start and end, which can be used to limit the index range, which is counted over. So for example, if I set the start to be the default of 0, and if I set the end to be 2, and let me just change the character to be a substring, notice that the count is 0. because we're counting from 0 and going up to 2, but not including 2. And we see that this character is at index 3, so if we count up to index 4, and excluding index 4, then we'll encompass index 3 and we'll get a count of 1. The method index will retrieve the index of a substring. So if we have a look at the index of this particular character, we see that its index is 3. And the method index will only retrieve the first instance of the substring. So if the substring occurs multiple times, you're only going to get the first index. So once again, it's got start and end, which can be used to limit the range. So for example, if you find the first index, then you may limit the range to the value 1 after this index, and then continue on the search. Notice that index gives a value error when the substring is not found. So there's an associated method called find, which essentially does the same thing as index if the index appears. And if the index doesn't appear, it returns the value -1 instead of an error. So this is sometimes a safer method to use because it won't flag up the error and halt the execution of your code. So we've examined the string in the Variable Explorer as a tuple going from top to bottom, but text is typically written from left to right, and the index and find methods operate from left to right. However, we have the equivalents that operate from right to left. So for example, if we have a look at the string hello, and we use find, and look for the character L, we get L at index 2, 0, 1, 2. And if we start at an index of 2, we're still going to find the same value because we're inclusive of the start bound. So if instead we start at the index of 3, we find the L at the index of 3. And if we start the find at an index of 4, we get the value -1 because there's no substring L in the remainder of this string. So let me just assign hello to the variable text2, and I'm going to cast this into a tuple. So now what I'm going to do is use text.to.find L, and I'm going to start the search at an index of 1 and end it at an index of 4. So remember, we go up to 4, but we don't include 4, so we're effectively searching for L within these 3 characters. And we carried out the find operation from left to right. So instead of using find, we can use right find, and we're going to carry out the operation from right to left. Note that the start and the end index used to construct the reverse find operation are the same and are expressed from the perspective of the string going from left to right. The right index and the right find behave in the same manner when the substring is found, but differ when the substring isn't found. And essentially have analogous behavior to their left to right counterparts. So in addition to find an index, we have the string methods startswith and endswith, which return a Boolean value if the string starts with a prefix or ends with a suffix, respectively. And these methods have consistent optional parameters, start and end, which can be used to limit the indexes that the starts with or ends with search is made over. So for example, if we use the first word as a substring, we can see that it starts with this. However, if we set the index to be 1, we can see that it doesn't start with this because the range excludes the first character. But we can see that it starts with the substring without the first character. And we can use endswith to see if the string ends with the last word followed by exclamation mark. And we can limit this range from a start index of 0 to an end index of -1. And note that we start at the start index and we go up to what we don't include, the end index. So in this case, the end index is -1 and we don't include the last character. So we can see that this is equivalent to the last word, and it doesn't have the exclamation mark. So we also have the text method replace, which can be used to replace an old substring with a new substring. And notice that it's got the optional parameter count, which has the default value -1, which means all instances of the substring will be replaced. So for example, if we take old being the first word, and new we can convert old to uppercase. So now we can use text.replace and replace the old substring, which exists in text, with the new substring. And notice that the first word is now in uppercase and the rest is as it was. So in Greek, the letter epsilon can be written using two different styles. So if we assign the current style that we're using to old and the other style to new, and now if I just copy the value of text into the IPython console, I'm going to enclose it in parentheses, and I'm going to use string replication on it, and then I'm going to use replace. So the default count value for replace is -1, so all instances will be replaced. However, if I set this to 2, notice that only the first 2 replacements are made and the last one is left unchanged. So a multi-line string can be created using triple quotations. And one thing to be careful about when using a multi-line string is the spacing between the quotations. So for example, if we want to create a multi-line string with the Greek greeting 4 times, what we would input is the following. And if we go ahead and print this, we can see that we get hello world in Greek 4 times. Now notice that if we change the spacing to make it look a bit more elegant, so if we use tabs here, and each of the 3 quotations are on its own line, then when we actually print this, these tabs and these new lines are incorporated into this multi-line string. And one of the most commonly used use cases of a multi-line string is for the docstring, which you've seen at the top of the new script file. And in this case, we're going to create a docstring for a function. And quite often, docstrings for functions are written in brief during development. So you might have a brief single one-line docstring. Typically, you'd still use triple quotations because you can later expand it. Notice that Spyder also has the generate docstring, which gives a template. So we can fill in this template. And now we have a docstring for this function. So let's create another function now. And this function is going to have an optional parameter, which is a string, and this string has a default value. So notice that when we select generate docstring, that this default value is included within this docstring, and this is a string literal. And for this reason, we generally prefer use of triple quotes instead of single quotes for a multi-line string, because a multi-line string is likely to contain a string literal. And this is particularly prominent when you use a multi-line string to create a docstring. So the fundamental unit in a string is a Unicode character, and we can import Unicode data and determine the Unicode version. And Unicode has a very large technical guide outlining the characters supported and how these characters are grouped together. And one of the most basic groupings is called ASCII, which is an abbreviation for American Standard Code for Information Interchange. And because Americans speak English, it's essentially the characters used in the English language. So we've got the uppercase and lowercase English letters, and then we've got the numbers, and then we've got punctuation symbols, and then we've got spaces, so we've got the space, and also the tab. So these are known as printable commands. Now ASCII is an encoding system which contains the commands for essentially a very primitive computer. And computers essentially originated from typewriters. So a typewriter's function is to print text onto a piece of paper. And basically the piece of paper gets fed through here. And as you type, you move from left to right. And then as you get to the end of the line, you need to return the carriage back to the left and feed the paper through. So although this is quite primitive, the way that we type code into a Python script file is similar, and a lot of these commands are still commonly in use. So if we have a look at the ASCII table, we can see that the first 31 commands are these non-printable commands. And we can see in a bit more detail that each of these commands is instructing the device to do something. Then we have the printable characters, and you'll recognize most of these from the English language. Notice that some of the characters, such as the space, have a symbol here, just because otherwise it would be invisible. And if we have a look at the left-hand side, we've got our numbering system in decimal. However, there's a couple of other numbering systems, particularly hex and binary. So these numbering systems are more appropriate when working at the hardware level. So if we conceptualize the memory of a computer is essentially a switch. So a switch has two values, off or on, and we typically group switches into groupings of 8, known as a byte. So 2 to the power of 8 gives 256 combinations. And to conceptualize this, I'm going to place a switch on the breadboard. So the switch has the values 0 or 1. So we can toggle this between 0 and 1 respectively. And if we combine 8 of these switches together, we can have a look at the combinations. So we've got the combination 0, the combination 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. So quite often what we actually do is treat the byte as two separate halves, and we assign a character to each of these 16 combinations. So this would be 0f, and in binary this is 0, 0, 0, 0, 1, 1, 1. And in a text data type known as a byte, what we have under the hood is a byte for each ASCII character. And the sequence of bytes can be represented in hexadecimal, or it can be represented by each ASCII character itself. So the following forms are equivalent. So the ASCII characters themselves only occupy up to half a byte, which is 2 to the power of 7. So this has the last value in decimal of 127. So if we go to the top, we've got this binary sequence corresponding to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then because we run out of numbers, we use characters, so A, B, C, D, E, and F. And we've got unique character for each of the 16 combinations. And because we're using zero order indexing, we're inclusive of 0 and exclusive of 16, so the last value is 15, which is represented by F. So a byte is 8 bits, and this is 256 combinations. Typically, a byte is split into 2, and each half byte is represented using a hexadecimal digit. And each hexadecimal digit has 16 combinations, and 16 times 16 is 256. Okay, so we can examine the bytes instance hello in a bit more detail. So we can input this by having the string hello with the prefix b, and this is a byte string. And we can use the method hex to view this as a hexadecimal string. And what this means is we're inserting the bytes with the values 64, 65, 6C, 6C, and 6F. So we can use \x to insert a 2-digit hexadecimal escape character, i.e. a byte, and notice that this returns the string hello. And now I'm just going to change the lowercase h to the uppercase h. And from the ASCII table, we can see the byte in binary as well as in hexadecimal form. So we've got uppercase h, lowercase e, lowercase l twice, and then lowercase o. And recall that this can be conceptualized as the following 5 bytes. And now for simplicity, I'm just going to have a look at a single byte corresponding to the character A. So notice to the left that we have the ordinal decimal value as 97. And we can use the ordinal function to retrieve this. We can also use the hexadecimal function to retrieve a hexadecimal string. So this is represented as a string of the number, because when we use this hexadecimal number, you can see that this hexadecimal number is recognized because it's highlighted in yellow. Notice that the return value is returned as a decimal integer, and this is because it's an int instance, and the default representation for an int is in decimal. And the binary function likewise will return a binary string, which is once again an integer, and the integer uses the default formal representation of the base of 10. The non-Datamodel identifiers in the string class are all callable, so they're all methods. The string doesn't have any additional attributes. These have been compartmentalized into the string module. So if we import string and type in string dot, we see a number of commonly used strings, such as the grouping of ASCII letters, ASCII lowercase, ASCII uppercase, punctuation, digits, and these are the decimal digits, and then we've got hexadecimal digits. So typically we use the lowercase characters for the other 6 values. However, the uppercase characters are also recognized and seen as being equivalent to their lowercase counterparts when used as a hexadecimal digit. So it's quite common to use one of these groupings to see if a letter is in the grouping. So for example, we can check if A is in ASCII letters, and this is true, and we can check if the accented alpha is in ASCII letters, and this is false. So we've also got string.whitespace. So this includes the space, The /t is a tab. The /n is a new line. The /r is a carriage return. And the escape character OB is the vertical tab. And the vertical tab isn't commonly used, and if I try to print this, it actually doesn't render properly. The last whitespace command is 0c, and this is for the form feed. So if we conceptualize this IPython console as a scroll of paper going through a typewriter, and we use a form feed, what we are essentially going to do is pull this piece of paper through until the next prompt is at the top. So in other words, it effectively clears the IPython console, but it doesn't remove all the variables created. So let me just type that in again so you can see the effect once again. So we've seen that we use the / to insert a byte or an escape character. So the / can actually be used to insert a / as an escape character alongside a single and double quotation. So in this case, designating the / and a single quotation and double quotation as part of the string. So if we use the data model attribute file, we'll get the file path of the string module. And let me just navigate to this location within Windows Explorer. So the default separator for a file and folder in Windows Explorer is the /, which we've seen in Python is used to insert an escape character into a string. So if we go ahead and copy this file path and enclose it in single quotations, we're actually going to get an error message. So /u is an instruction to insert a Unicode escape character, and it expects 4 bytes, so this is going to be 8 hexadecimal digits. So what we need to do is change each of these /s to 2 /s, i.e. the first / is an instruction to insert an escape character, and the escape character is going to be in the / itself. So notice that this now works. And we can also prefix the string with R, which creates a raw string. So in a raw string, the / is part of the string and is not an instruction to insert an escape character. There's a subtle difference between lowercase and uppercase r. Now it's not shown in the Spyder IDE, but in some other IDEs, the lowercase r will be used for a regular expression, and the uppercase R will be used for a file path. So you can essentially see the difference in syntax highlighting when the uppercase R and the lowercase r are used in another IDE such as Visual Studio Code. And hopefully this difference will also be apparent in Spyder in a future version. So we've used the print function a few times now. Let's actually have a look at it in a bit more detail. So if we highlight it and press Ctrl and I, we can inspect it. So *args means there's a variable number of positional input arguments. And then there's the optional parameters, separator and end, which specify the separator between each input argument and the ending of the print statement respectively. So we can print text, and we can just, for example, print text, comma text, and we can print text, comma text, comma text. So using 1, 2, and 3 positional input arguments. And we can change the separator from its default of a space to a tab or 2 tabs. And we can also change it to a new line. So if we use multiple print statements, we can also have a look at the effect of the end. And by default, it uses a new line. So the following would be the default behavior, but if we change one of these to just a space, notice what happens. So I'm just going to clear up the namespace, removing old variables that are no longer going to be used. The string class has a number of case methods. Typically, these methods don't require additional input arguments because all they need is the instance data to work with. So capitalize will return a capitalized version of a string. So that's essentially the first character will be capitalized and the rest of the string will be left as is. So notice in this case, it's already been capitalized, so the string hasn't changed. So just for clarity, I can create this string, hello world, and capitalize it. And notice that you need to use the American spelling. So the first character is capitalized and everything else is left as is. So there's also the case method title, and this will capitalize every single word. So the method recognizes words because they precede spaces. So I can use title on the string instance text. And we also have the case methods upper and lower, which return an upper version of the string and a lower version of the string respectively. Now there's an additional case method called caseFold. So remember earlier we discussed that there were two variations of this character epsilon in Greek, and we replaced one with the other. And because this string method replace returns a string, which is a string instance, we can call another method from it. So we can call the method lower from this. And we can check to see if this is equal to the string that we've pasted using the lower method on it. And we can see that this is true. But when we remove the replace, we can see that this is false. So instead of using lower, we can use caseFold. And what this does is it essentially makes the string lowercase and replaces any variations of characters with their most common variant. And so the expression above will use the most common version of epsilon for the string on the left and the string on the right. And it will see that these are equal to each other. And just for clarity, we can just see what caseFold does on each of these individual strings. And we see that we get the same epsilon for both of them. So we can see that the value returned in both cases is the same. We also have the case method swapCase, which swaps lowercase letters for uppercase and uppercase letters for lowercase. So here we've seen capitalized caseFold, lower, swapCase title, and upper. So the methods lower and upper essentially use a custom translation table to translate lowercase letters into uppercase letters, for example. So if we look at the help of the string class, we see that we have this static method make translation table. And it's a static method because it's essentially just a regular function that's conveniently found in the namespace of the string class. And it's found here because the translation table is used with the string method translate. So this is the most convenient place to put it. So notice that this method is not called from an instance, but it's called from the class itself. And I'm going to translate the lowercase ASCII letters to uppercase ASCII letters. So we've created this lower to upper translation table, and this is essentially mapping, which is also known as a dictionary. And if we open it up, we can see on the left that we've got numeric keys, and these correspond to numeric values. So these integers are shown in decimal, but We know we can also conceptualize them using hexadecimal or binary. However, they are the decimal integers corresponding to the ASCII characters. So now that we've got this translation table, we can create the string hello world and translate it using this translation table. And then, as expected, every ASCII character that was lowercase has been translated to its uppercase equivalent. So the string has a number of Boolean methods which return a Boolean in response to a query. So essentially we have this text is title, and in this case the query is false, so we get false. So if we use the text.title method, we'll see it in title case, and then we can check if this is title, and we get true. And we can also check if text is in uppercase, which is false. So we can use text.upper to get it in uppercase, and then we can check this, and we can see that this is true. And we can check to see if text is lowercase, and this is false. So we can use text.lower to view this in lowercase and then check whether this is lowercase and this is true. We also have the query is identifier, and notice that this is false. And this is false because we've got spaces and a punctuation mark which aren't allowed in identifiers. If we actually take the object name text and make a string of this and check if this is an identifier, we can see this is true. And obviously this is true because we are using this as an identifier, also known as a variable, which displays in the variable explorer. So identifiers cannot have a space because the Python interpreter will think the space means the separation of two identifiers. And identifiers can't have an operator because when this is used in the IPython console, the IPython console will attempt to use the operator. The underscore is accepted as being a valid part of the identifier. And we can also add a number to the identifier. Notice, however, we cannot begin with a number. We can begin with an underscore, and we can begin and end with a double underscore, as we've seen in the data model identifiers. We can also use all uppercase for an identifier, and this is commonly done for a constant. There is also the string method is printable. Now this isn't restricted to only the ASCII characters. Notice that text contains Greek characters that are all printable. So text is printable and it contains non-ASCII but printable characters. So if we use a hexadecimal escape sequence to one of the non-printable commands, such as this null character, we can check to see if this is printable, and we get false. We can use the isASCII method to check whether each character in the string is an ASCII character. And we're using Greek characters which are non-ASCII, so this is false. So notice that hello space 123 exclamation mark is ASCII. We also has is alphanumerical, and this is false because it's got a space and an exclamation mark. If these are removed, this is true. We also have is alphabetical and is space. So for is space, this means that every character in the string is one of the strings in string.whitespace. So there's a number of identifiers that are used to check whether the string is essentially a number. There's is decimal, is digit, is numeric, and is alphanumeric. And it's best to see the differences in these using examples. So we can see that is decimal is the most restrictive. And we can see that is digit has a few more additional true categories. And we can see isNumeric, once again, has a few more additional true categories. And then we can see isAlphanumeric will accept all the numeric properties from isNumeric, as well as alphabetical values. So we also have some methods to center and justify text. Notice you need to use the American spelling of center. So we center the text using a width, and we can optionally specify this fill character. Note that we need to specify these parameters using positional input arguments. If we attempt to use a named parameter, we're going to get the type error informing us that this method takes in no keyword arguments. And recall this right slash means that any input arguments before it are to be provided positionally. So we can also left justify and right justify the text. There is also the strip method, which is normally used to strip white space around a string. So for example, if we have this string, hello with white space around it, and we use strip, notice that we return the string hello. So there's also a left strip and a right strip. So you can see that the left spacing and the right spacing are stripped respectively. We can also strip a different character. Notice that strip will only strip at the start and end of the string, and this character found in the middle of the string is not stripped. There are also the string methods remove prefix and remove suffix, and in this case you need to be more precise and specify the exact prefix you want to remove. So notice that this is removing only 1x, 2x and 3x's respectively. And if we use the ordinal function to return the ordinal value corresponding to the character 3, we can use the binary function to view this as a binary string. So we can remove the 0b prefix, and because this is a byte which has 8 values, we can use the zero fill method to fill this up to 8 spaces. And this helps us conceptualize the full byte. The method partition will partition a string using a substring into a 3-element tuple. So the 3-element tuple is going to contain 3 strings, essentially the substring before the partition substring, and then the partition after the partition substring. So partition operates from left to right, returning a 3-element tuple. Right partition operates from right to left, returning a 3-element tuple. And you can see the difference here because I placed a substring twice within the string. The string method split will split the string into a list of strings, and each string typically corresponds to a word using the space as a default split character. So there's also a right split, so we can go ahead and use that to get reverse words. So the behavior of both initially appears to be identical, and the difference is only seen when we use some of the optional parameters. So we've got the separator and the maximum split. So the difference is only really seen if you use the maximum split. So I've set the maximum split to 2, and this should be words. So 2 splits will actually give 3 substrings, so let's reduce that down to 1. And now let's have a look at the reverse split. and compare words with our words. So we can see the difference in the left split and the right split. So if we set the delimiter to be a space, we can call the join method from it, and we can join this list of words. So the delimiter doesn't necessarily need to be a space. We can use a different character. And in this case, the hash only appears once because recall the second and third word are joined together in the second substring. And I'm going to create a multi-line string using triple quotations, and it's going to contain this string literal 4 times. And if I have a look at the formal representation of the string, I can see I've got the escape character /n new line, and I can use the string method split lines, which splits the lines using this character \n. And now I've got a list of substrings where each substring was a new line within this multi-line string. And now I'm going to have a look at making a string of a function. So I'm essentially going to make a multi-line string using the function definition and then a tab, and then the calculation, and then a tab, and then the return value. And then I'm going to close the multi-line string. So if I print this, notice that it prints similar to how we would type this within the script editor. We can use the method expand tabs to expand the tabs to a specified number of spaces. So for example, we can have 8 spaces or 4 spaces, and we can see the difference when we print these out. So when we had a look at a string of a file path, we've seen that we could make it into a raw string, and we've seen that there was the uppercase R, which was preferred for a file path, and there's lowercase r, which is preferred for a regular expression. So Python has a regular expressions module, and essentially this contains a number of methods to search for a substring using a regular expression. So you need to construct a regular expression in the form of making a pattern. So this can be a pattern for an email, a pattern for a number, or a pattern for a website. And the syntax for a regular expression is a bit more advanced, which is why it's compartmentalized into a separate module. So I'm not going to delve into too much detail. However, essentially you can see just by searching through the documentation what each of these individual elements mean in the raw string. So I don't want to get too wrapped up in details and over-explain the patterns to the right. However, you can see that these are for an email, a number, and a website. And we can use the findAll method to find all substrings which match this email pattern. So I've just forgot a comma. So if we have a look at email search, we've got a list of 2 strings, and these are the 2 emails. And we can repeat this for the regular expression of the telephone number. And now we've got a list of a string corresponding to that number. We can also do the same for the website. And now we've got a list of a string corresponding to that single website. So the string class is a class which has a Unicode character as its fundamental unit. There's another text-related class called the bytes, and this has a byte as a fundamental unit. And we've already kind of visualized what a byte looks like, so you should have a good conceptualization. So if I just have a look at its directory and then just reorder this and compare it side by side with the string, we can see that there's a high level of consistency because both classes follow the same design pattern, and there's just a small number of differences between the actual identifier names. So the Unicode string has a Unicode character as a fundamental unit, and this means we can press Windows and full stop and use any of these characters in the emoji panel within a Unicode string. So the Unicode string has great flexibility and is easy to use. So the string method encode can be used to encode a string into a bytes instance. And in order to do so, we need some sort of encoding table, which is essentially a mapping which encodes each specific character into a byte sequence. And note that the initialization signature of the bytes class is very similar and can be used to cast a Unicode string into a bytes instance. If all the characters are ASCII, then we can just prefix the string with B to create a bytes instance. So recall that ASCII has non-printable and printable characters, and these occupy up to half a byte. So when the byte maps to an ASCII printable character, the ASCII printable character can be used to represent the byte in the byte string. And the byte string has a hexadecimal method which returns each byte as a pair of hexadecimal digits. So in this case, the single character A has the hexadecimal digits of 61, and this is the integer 97. And recall that this can also be represented in binary. Unfortunately, the Spyder IDE doesn't change the color coding for 0B and 0X as seen in other IDEs such as Visual Studio Code, which makes this a bit more apparent. So we've got the binary form, so recall we can use the string method remove prefix to remove the 0B prefix. And we can also use the string method zerofill to fill this up to 8 spaces so we can see all 8 bits in the byte. So notice that the first bit is 0, and this is because ASCII only spans over half a byte. For the other half of the byte, there were regional encoding tables. So for example, we've got Latin1, which was used in Western Europe. And basically it's the same. You've got the same ASCII set, and then you've got these extended ASCII codes. So a number of these are unused, and then you've got commonly used characters such as the pound sign, which is used in the UK. And then there's some other accents used in Western European countries and a small number of mathematical symbols. So there was also Latin2, and this was used in Eastern Europe. So once again, the start of it is the same as ASCII, and then the second half basically has a slightly different set of characters that are used for Eastern European languages. So we also had Latin3, which was used for South European languages. So once again, ASCII occupies the first half of the byte, and the second half of the byte uses a different set of characters. There was also Latin4, which was used in Northern European languages. So once again, the first half is the same as ASCII, and in the second half uses a slightly different character set. And then there were other languages such as Greek. So once again, the top half of the byte was in ASCII, and then the second half is characters used for the Greek language. So in the past, you would install an operating system such as Windows, and then during installation, you would select your language, and this would use the appropriate translation table for your language. So if we have a look at the pound sign, we can attempt to encode it into ASCII. And notice that we get this error because the hexadecimal value A3 is larger than 128. So it's a non-ASCII character and cannot be encoded into ASCII. So if we have a look at this hexadecimal value A3, we see that it's an integer that's larger than 127. So it's out with the ASCII range. Recall that range is exclusive of the stop bound, so that's why it shows 1 to 8 here, with the last value being 1 to 7. And if we have a look at this in binary, we see that the first bit is 1, which means it's out with the ASCII range. So we've seen that the pound is in Latin1, so if we encode to Latin1, we get this A3. And if we try to encode to Latin2, we get this Unicode encode error because it doesn't exist in Latin2. So now we can try Latin3, and it exists here, so we get A3. We can try Latin4, and once again we get this Unicode encode error because it doesn't exist in Latin4. And we can try Greek, and once again we get A3. So we can use the hexadecimal escape character, A3, to insert this A3 byte into the byte sequence. And notice that it displays in the following form. Now, if we have a look at an ASCII character, such as the exclamation mark, and express this in the same form using /x and then 21, notice that the formal representation displays the ASCII character instead of this byte. So the formal representation of a byte sequence containing ASCII and non-ASCII characters can sometimes look very confusing. So for example, if you've got A and then /x A3 and then A, you should understand what A is an ASCII character and what A is being inserted as part of a byte sequence. So let's have a look at this character and encode it to Latin1. And this gives a byte instance, and we can decode this into Latin1. Now, in the early days of the internet, people would write a website using one encoding table, and unfortunately others would read the website using their specific regional settings on their computer, and often a lot of the characters would be substituted for a completely different character. And notice that this would only happen to non-ASCII characters. So pretty much if someone wrote the website in English, most of the characters would display as expected. However, if they were using different languages, then maybe only half the characters would work. So the ASCII characters would display as expected, and the other characters would be substituted by something else. All of these encoding tables encode a character to a single byte. So in the bytes class, the byte is the fundamental unit, and the length of these byte strings is going to be the length of the bytes. And because it's 1 byte per character, in this case the length is going to be the same. So notice that if you use a hexadecimal escape sequence in a string, that it's essentially going to insert the ASCII character when it's a ASCII character. And in this case, because I have Windows installed using UK regional settings, it's going to use Latin1 for a non-ASCII character. So for instance, A3 is the pound sign and B0 is the degree. So as the world connected via the internet, it became apparent that we needed a universal format, and this led to the creation of UTF, a Unicode transformation format. So the first version was UTF-16, and the 16 essentially corresponds to the number of bits used for encoding. So recall that there's 8 bits in a byte, so 16 means you've got 2 bytes per character, and recall that a byte's represented using 2 hexadecimal strings. And therefore a character which is represented using 2 bytes has 4 hexadecimal strings. So let's encode this to UTF-16 big endian. So this is 0-3 for the big byte and 9-3 for the little byte. And we can use the bytes method hexadecimal to make this a bit more clear. So this is analogous to the way that we count. So for example, if we take the number 10, what we have is the most significant digit, or the big digit, first, and then the least significant digit second. Now, unfortunately, many processors actually handled bytes in a different manner, and they use little endian instead. So this would put the least significant byte first, followed by the most significant byte. So this is equivalent to representing 10 as this form 0-1 instead of 1-0. And this essentially led to a lot of confusion because people would expect to use big endian, but the system would use little endian, and essentially you would get the same problem as you've seen before with character substitution, because the wrong translation table was used during decoding. So in order to get around this, there was another UTF-16 variant which used a byte order marker. So essentially an additional 2 bytes is added at the start of the sequence and indicates the byte order. So notice that the most significant byte is first, and then you've got the least significant byte. So this actually uses little endian. So after the byte order marker, you see the same 9-3 and 0-3 pair. And if we look at an empty string, notice that we get the byte order marker. So let's have a look at text, and let's attempt to encode this to UTF-16. So notice that this is quite hard to read. So you've got 2 bytes per character, and then you've got the byte which represents the space in ASCII. However, in UTF-16 it needs to be paired with another byte, and this is the byte 00, which is null. And you see the same thing for the next space, and a similar thing for the ASCII character exclamation mark. So if we have a look at this in hex, we've got the byte order marker, and then we've got each byte. And here we can see the space. And here we can see the other space. And here we can see the exclamation mark. And recall that this is in little endian, and we would normally conceptualize this as humans in big endian. So 2 bytes wasn't enough to encompass all the characters that we needed. So there was a move to go over to 4 bytes. And we've also got UTF-8, 32 big endian. And if we use the escape character /u in a string, then we can insert a character using an 8-digit hexadecimal sequence that's in the format of UTF-32 big endian. So in addition to big endian, we have the little endian. So instead of the pair 00, the pair 00, the pair 03, and then the pair 93, we've got the pair 93 and then the pair 03, the pair 00, and then the pair 00. So the byte order's reversed as we've seen before. And UTF-32 once again uses a byte order marker, and this time it's got to have 8 hexadecimal values because it needs to match the length expected for UTF-32. Otherwise you can see that it's little endian. And we can have a look at the byte order marker on its own by examining an empty string. So we've seen that we can use the escape sequence U to insert a Unicode escape character. And notice to do so we need to insert all 8 digits. We can't omit any trailing zeros because this will give us a syntax error. Notice that when you try and make a string of a Windows file path, in the users directory you've got left/u, and this expects you to insert a Unicode escape character, and that's why you get this error message quite often when you're attempting to use Windows paths. So one of the drawbacks for UTF-32 was the number of trailing zeros needed for an ASCII character. So another standard called UTF-8 was created, where essentially an ASCII character would occupy 1 byte. Other characters such as Greek characters would occupy 2 bytes. Chinese characters would occupy 3 bytes, and additional characters such as emojis would occupy 4 bytes. So we've got 8 bits in a byte, and because the ASCII characters only occupy 1 byte, this standard is called UTF-8. So the ASCII sequence is essentially a subset of UTF-8. However, UTF-32 and UTF-16 are not subsets. So if we essentially have a look at these in binary, we can see that there's patterns for each of the bytes. So when we're inserting a multi-sequence byte, what we have is this 110 for 2 bytes, and then the subsequent byte starts with 10, and then for 3 bytes we've got 1110, and then each subsequent byte starts with 10, and then for 4 bytes we've got 11110, and then each subsequent byte starts with 10. So notice that the multi-byte sequences typically start with 1, and an ASCII character would typically start with 0. So UTF-8 is the current standard, and it's the standard used for a Unicode string. Now, unfortunately, at the time of release of UTF-8, Microsoft prepared for issues and created a version called UTF-8 signature, which includes a byte order marker. And therefore, unfortunately, it's quite common to find this byte order marker when you save a file using a Microsoft program such as Excel, using UTF-8 signature, and then you try and read it in using UTF-8. It's becoming less common, but if you're using an old Microsoft product and something that's to current standard, you may encounter this problem. So let's use the current standard UTF-8, and let's create the following byte string from text. Notice that the variable explorer encodes this using UTF-8, so you see the characters. Notice that the length of the Unicode string text is 14, and the length of the byte string btext is 25. And the reason for this is the two text related sequences have a different fundamental unit. One of them has the Unicode character, and the other has the byte as the fundamental unit. And we'll also see a difference when we index. So if we have a look at the first value in each case, which is index 0, we see we get the Unicode character for the Unicode string, and we see we get 206 for the byte string. So 206 is a number less than 256 and maps to a byte. So this is CE, and if we type in /xce within a string, we get the Latin1 character. And this isn't what we actually want in this case, because it's going to use multiple bytes to represent a character. So if we make a slice of a string, we're going to get a substring. And if we make a slice of a byte string, we're going to get a sub-byte string. And the Greek character uppercase gamma maps to these 2 bytes in UTF-8. And we can see the difference in fundamental unit in a bit more detail by casting both of these sequences to a tuple. So notice that the value is essentially a byte here, so it's an integer between 0 and 255. And in the case of the Unicode string, the fundamental value is essentially a Unicode character. So one thing to keep in mind when slicing a byte sequence is that you may actually get an incomplete sequence. So you're not going to have everything for this specific character because this character is encoded over 2 bytes and we only have 1 byte. So if we attempt to decode this, we're going to get the Unicode decode error. And this is because we're expecting this second byte and we don't provide it. Both the string and bytes class are immutable, which means once a string or bytes instance is created, it cannot be modified. And there's a mutable counterpart to the bytes class called the bytearray. So this follows the design pattern of a mutable sequence, and it essentially has all the identifiers seen in the immutable version, plus the identifiers that are mutable. So if I have a look at the directory of identifiers for the bytearray class and compare this to the byte class, we can see that most of the mutable methods in the bytes class are consistent in the bytearray class. There are some differences such as hash, which is essentially set to none in the mutable version because a value that changes cannot have a hash value. Notice that instead of just having getItem, we've now got setItem and deleteItem. And instead of just add and multiply, we've got inplace add and inplace multiply. And then we have the method copy, which will create a copy of the instance. And then we've got the mutable methods append, clear, extend, insert, remove, and reverse. So all of these mutable methods have no return value and modify the instance in place. Pop is the unique method that mutates the instance and has a return value. So a byte array instance is normally constructed by casting a byte to a byte array using the byte array class. So let's assign this to a variable, and notice that it just displays on the variable explorer as byte array object, so it's not fully supported on the variable explorer, and this is because it's not really commonly used. So length is consistent between bytes and byte array, reporting back the number of bytes per instance. The byte array also has this allocation, so typically one more byte is allocated to it, and this just speeds up some of the mutable methods such as append. We can use the builtins function identification to retrieve the identification value of an object. So let's have a look at the identification of BA text, and let's also have a look at it in hex. So we can index into it using an index of 0 to retrieve the first byte. And we can decode a byte array into Unicode string using the decode function. So this is consistent behavior to the bytes class. And let's now have a look at the first index. So this has this value 93, and this was 147. So what I'm going to do now is index into this and replace it with 148. So notice that I've performed an assignment, and this means that BA text has been modified. So notice that this 93 is now 94. And if I have a look at the identification, we can see that it's the same. So it's the same object, and it's been modified in place. So that's what mutable means. Mutable means modify the object in place. And now if we decode this, we can see that this character has changed from uppercase gamma to uppercase delta. We can also delete one of these bytes. So for example, if we delete the first byte at index 0, notice that we no longer have the CE. And if we try to decode this to a Unicode string using UTF-8, we're going to get this Unicode decode error, and this is because one of the characters has an incomplete byte sequence. So if we delete the first index now, which is now going to be 94, then we've deleted the 2 bytes that corresponded to what was previously the first character. So now the decoding works, and we can see that we've lost the first character, and we can see that this byte array has been mutated in place. So a mutable method should not be confused with reassignment. So notice that when reassignment is used, that the identification number changes. So think of it as pulling the label off this byte array that had the identification number ending in 92 and placing it on this new byte array which has the identification number ending in 36. And since this is a new instance cast from the bytes instance, we've got the first character back. So this is the pair CE and the pair 93, and this was the Greek uppercase gamma. So let's have a look at the bytes instance btype, and what I'm going to do is I'm going to use the add operator to perform byte concatenation, and I'm just going to concatenate the byte corresponding to the ASCII character, the exclamation mark. So notice that a return value is given, and this means that the bytes instance btext is unmodified. So now I'm going to have a look at the plus equals operator. So what this does is it performs a concatenation and then performs reassignment to the variable name btext. So if we have a look at the identification of btext, we can see that it's a different object. So essentially the object name btext, which can be conceptualized as a label, was peeled off the bytes instance with the identification ending in 256 and placed on the bytes instance with the identification ending in 440. So let's now have a look at the mutable byte array. And remember, although this is mutable, it's got both the immutable and mutable methods. So we can use the add operator to perform byte array concatenation. And notice that this is immutable because it has a return value, and the byte array instance BA text is unchanged. The byte array also has the mutable counterpart, which is the in-place add. So if we have a look at BA text, and instead of using plus, we're going to use plus equals. So initially this looks the same as using plus equals with the immutable byte array, which performed two operations. It performed the concatenation and then assignment. Notice for the byte array, however, that the object ID is unchanged. So we've not actually performed any reassignment. We've mutated the byte array in place directly, so it's the same object. So let's have a look at the ordinal value of the exclamation mark, and we see it's the decimal integer 33. And we can use the byte array method append to append this byte to the end of the byte array. So if we have a look at the byte array now, we can see that we have this additional exclamation mark as expected. So append essentially allows us to add one additional byte to the end of the byte array, and this byte is normally in the form of an integer, in this case a decimal integer. We also have the method extend, and this can be used to extend a byte array using another byte array. So for instance, we can extend this using the byte array that has the ASCII string hello. So once again, we see the byte array is mutated in place, and this method has no return value. We can use the method insert to insert a byte at a specific index. So let's just view this byte array as a tuple. So what I'm wanting to do is insert a new byte at index 2. So I'll once again just insert the exclamation mark. And once again, we see that this mutable method has no return value, but we can view BA text in the console and see that it's been mutated in place. Now, because the tuple is immutable and was cast from the old byte array, we need to recreate this tuple in order to see the changes. So now you see at index 2, we've got the value 33, and every single other value has moved up an index by 1, and we can also see that the length of this tuple is 1 longer than it was before. So we've also got the mutable method remove, which can be used to remove the first instance of a byte in a byte array. So in this case, this will remove the value that was at index 2, and then everything will be shunted back down by an index, and the length will be 1 less than it previously was. We also have the mutable method reverse, which can be used to reverse the order of the bytes in the byte array. So once again, this is a mutable method and there's no return value. We can view the results in the console and we can see that this byte array has indeed been reversed. So let me just have a look at the identification of BA text. And what I'm going to do is I'm going to use the immutable method copy, which returns a copy of the byte array. And notice this copy has a unique identification because it's a separate object. So now I can have a look at the mutable method clear and I can work on the copy. So once again, this is a mutable method, so has no return value. So we can view the results in the console and we can also see that the original byte array BA text is unmodified. And I'm just going to use the mutable method reverse to reverse the order to the way it was previous. So notice that BA text 2 is an empty byte array. Although it's empty, we can use the mutable methods append and extend to append a byte or extend it using multiple bytes. So notice that all the methods used have either been immutable with a return value or mutable and modified the byte array in place and haven't returned anything. There's one unique method called pop, which is mutable and returns a value. So what pop essentially does is it pops off the last byte, returning it and mutating the byte array in place. So notice that essentially this O has been popped off. So we can use the hexadecimal function to view this byte as a hexadecimal string. So in this case, it's 6F. And if we just have a look at the ordinal value of the ASCII character O, we get 111, which matches the return value because this is the byte that's been popped off. So pop has an optional input parameter, index. So we can select 1 as being the first index. And because this has a return value, we can assign it to an object name. So this returns the byte to this object name and mutates the byte array in place. So you see that the byte with the hexadecimal value 93, which was previously at index of 1, is now not present in this byte array. And if we have a look at the hexadecimal value of this popped byte, we can see it's 93. So the byte array is actually at a stage where if we attempt to decode it, we're going to get an encoding error because we've got an incomplete byte sequence for a character. So this is one thing you need to watch out for when you're using mutable methods on the byte array. And as a beginner, you're not likely to encounter the byte or a byte array class too often. Most text-related data should be handled using the Unicode string class because this doesn't separate the encoding from the content itself. And it's much easier to work with this using the Unicode character as a fundamental unit opposed to a byte.